Unfortunately, because of our cultural aversion to everything fat, that has translated to an aversion to, or even a hatred of our fat cells. And the reality is, they're not there by accident, and they're not there to hurt us. There are, in fact, diseases of people who have a genetic inability to make fat cells. And they are exceptionally lean. I mean, they are ripped, as you might say. I mean, they are incredibly lean, and they're incredibly sick. They end up getting fatty tissue, fatty liver, fat storage in their muscle and bones, and they develop all kinds of diseases. So that's my weird way of introducing the fact that fat cells are essential. We need them. But wouldn't you know it, nowadays they've gone too far. And so the fat cell is a cell that is on the surface designed to store energy. So if there's an excess and the body has been signaled to store energy, and those are not the same thing. So there's energy to store, and the fat cells are being told to store it, then the fat cells will store energy for later use. But beyond the simple metabolic aspect, which we both know is the one most people are interested in, is the fact that fat cells are also a very prominent part of the endocrine system within the body. They release a myriad of hormones that do all kinds of things for metabolically beneficial, and not only beneficial to metabolism, like regulating appetite, but also regulating things as fundamental as fertility and reproduction. People don't appreciate that aspect of the fat cell. So in my mind, the fat cell's been given a bad rap. And I say that as a fat cell scientist, but at the same time, of course, it is at the center of so many of the cardiometabolic and chronic disease problems that we suffer from today that we didn't suffer from in previous generations. These so-called plagues of prosperity really can be, if you drill down, you find the fat cell at the base of so many of these issues. We call one of these depots white adipose tissue, and the other we can call brown adipose tissue. It is, in fact, because of a difference in color. One of the things we do in my lab is do fat biopsies from humans from around their belly, and we'll take out a little piece of fat from the belly, and it is very whitish, a little yellowish, and it's because it is primarily just fat. In a fat cell, it is almost entirely made up of a big drop of fat, like a bubble of fat. And it looks a little bit like Crisco almost, not quite as pristine, or like coconut oil. Maybe I'll put it that way. So that is white fat. And it's white, again, because of the incredible amount of fat. You can't see that is in those fat cells, and you can't really see anything else about the cells. In contrast, brown adipose tissue has small drops of fat within its cell, but it also has a very high preponderance of mitochondria. In mitochondria, the so-called powerhouse of the cell that everyone remembers from biology, from high school biology, the mitochondria are in fact a reddish, kind of brownish, darkly complected color. And the fat tissue that is so enriched with those mitochondria reflects that tissue. I mean, it literally reflects the light, I should say. And so it looks much more kind of reddish brown. And that not only do we see that stark difference in appearance, I mean, it actually looks more in color like muscle in color than it does other fat tissue. But with that difference in appearance is a profound difference in metabolism. And this kind of reflects the fact that white adipose tissue does indeed store fat very well. It's no surprise that white fat cells have a very low metabolic rate. Of all the cell types we've tested in my lab measuring metabolic rate in tissues, fat has by far the lowest. And then when we measure the metabolic rate of the brown adipose tissue cells, they are about 10 times higher. Its metabolic rate's about 10 times higher. In fact, it's in the same range as muscle cells. And so that's a pretty substantial effect. Now, the difference goes even one step further, that not only do the brown adipocytes have a much higher metabolic rate, but then the question is, what for? And that might sound a little academic of a question. What for? What is the metabolic rate for? By that, I simply mean, what is the cell burning that energy for? Because a cell will normally burn energy based on what the cell needs. And for example, muscle and even fat tissue, basically the muscle or the fat cell will say to the mitochondria, hey, mitochondria, the cell, all of the cell, we need this much energy to do our job. So give us this much energy. And that process is very coupled. That's what we call it. It's a very tightly coupled process. An analogy for this would be like someone who's driving a stick shift car and they're revving the gas and they see the RPMs driving up, really revving up, but they're keeping their other foot on the clutch, or the car isn't in gear. And so the speedometer, the actual amount of movement in the car, is nothing. It's not matched. So the RPMs are revving, but the speed isn't moving at all. That's uncoupled. That's when we've teased the two processes apart. So the instance I was just talking about, we're revving the gas and we're moving at the same time. The car is in gear and it's going down the road. Now, as I mentioned, in the uncoupled state, which is what we have with the mitochondria in the brown tissue, that's basically when the cell isn't demanding work from the mitochondria. The mitochondria just keep burning energy. So we're revving the engine, but not because the cell needs any work done. It does, but its needs are adequately met. In this case, the mitochondria in the brown fat cells are uncoupled, as we say. And in this case, they are just burning nutrients. They're burning fat. They're burning glucose for no cellular work that the cell needs done. It's just to create heat. And heat is a chemical like waste. A biochemical waste. It is sort of the sign of a wasting of energy, back into the universe, if you will, or into the atmosphere. But in the human body, that does serve a purpose, particularly when we're babies. A newborn baby has a relatively high amount of brown fat. So amidst all the chub on the baby is a relatively high amount of brown fat. And this is good because the newborn baby doesn't have enough muscle to shiver very well. And so it stays warm. If you lift your adorable little baby out of the bathtub, and he or she is going to stay warm, not by shivering, but by having all of this brown fat that suddenly turns on and starts chewing through nutrients just to create heat. Now, as we grow and our muscles grow and our body changes substantially, the relative amount of brown fat we have drops precipitously. And then much of the fat we continue to gain throughout our life is white fat. And that's okay. It works because if we're cold, we can shiver. However, we know that adult humans who have more brown fat or whose brown fat is more active, and we can talk about that, they are much more resistant to diet-induced weight gain and diabetes and other cardiometabolic complications. Now, on the human body, the white fat is basically the fat that you can pinch and jiggle. That's all of our subcutaneous fat and a little bit of fat within the abdominal space called visceral fat. And then humans have designed little pockets of brown fat kind of sprinkled throughout the thoracic cavity and up into the neck. Now that's not a lot, but my lab has found that when the white fat cells start consuming ketones as an energy source, they will actually enhance their mitochondria number, and the mitochondria will be more uncoupled. So we found in humans that when humans were in ketosis, their fat cell metabolic rate went up by 3 times. Now, that didn't get up to the 10 times higher that you see with brown fat, but still a tripling of the metabolic rate of fat cells is nothing to sneeze at. So it's like the white fat cell hasn't fully become a brown fat cell. It hasn't, and it can't, but it started to act a little bit like those brown fat cells. So it's not quite brown, but it's not quite white anymore. It's beige. And so we say that it was a beiging effect. So we found that the ketones have a beiging effect on the white fat, increasing their mitochondrial content and making the mitochondria behave in a more uncoupled state. Now, it's no surprise to people to learn that cold immersion will do the same thing, but that's, of course, a much less pleasant phenomenon by many standards than just being in ketosis through fasting or dietary control. But nevertheless, it does touch on the fact that you can leverage this biochemical phenomenon to have your fat cells start to really work in your favor in order to facilitate weight loss. So ironically, the fat cell begins eating its own fat as its metabolic rate has climbed, further facilitating fat loss. I know of no evidence to suggest that it can ever go all the way. I don't believe that could be possible. It would take a remarkable series of events and very likely nothing that the body could do on its own. Maybe someday some drug interventions or some injectable treatments. As the kind of cell biologist, fat scientist, there's a part of me that would think, oh yeah, that would be great to control obesity, but it would be catastrophic to things like appetite control and fertility, because brown fat cells do not behave in the same endocrine fashion as white fat cells. Like, for example, we've touched on a little bit fertility. Leptin, while we always think of leptin as only regulating appetite, it is utterly and totally essential to fertility. That's why if someone has a leptin deficiency, they are infertile. They're sterile. They cannot reproduce. You have to give them leptin in order for them to have a normal fertility capability. But brown fat cells produce essentially no leptin. And so it would be in a way catastrophic to the species, if we had people who were suddenly shifting over, not only catastrophic to the species, no reproduction, but even to their own health. Especially a woman whose body thrives on the remarkably dynamic cycling of the hormones that swing around so remarkably during a menstrual and ovulatory cycle. That would basically all be stopped in the absence of leptin. And that would be very bad for bone health, very bad for mental, emotional health. Now, I know I'm not a woman. I sometimes get a lot of heat that people suppose I can't talk about it. I'm an endocrine expert. I teach graduate level endocrinology courses, and I'm a fat cell scientist. So there are some things I can speak to as an authority, not because I'm a woman, but because I know hormones. Yeah, as much as it would sound like it's a good thing, let's kind of go all the way. Not that either of us is suggesting it. There would absolutely be consequences, and they wouldn't be good. I think that the sweet spot is through fasting and optimized lifestyle habits, you can sort of push the fat cell a little bit that direction, and you just get a little bit of that advantage, the metabolic advantage, without losing the fundamental necessity of the white fat in the first place. Brown adipose tissue is completely mingled through the ribs, then up into the clavicular space and up into the neck just a bit. It's an odd location, right? And it's certainly not something you can look at and say, well, gosh, my brown fat sure is getting big. You wouldn't see it because it's so enmeshed within the cavity itself. My speculation is that we have brown fat there in order to ensure all of the blood that's going to be coming up into the brain is warm in the event that the body is very cold. That if we're cold everywhere else, like you're immersed in an ice bath, you can shiver because you have muscles everywhere from your neck down. Well, we have no muscles up in our head. There's no muscles to shiver to keep the brain warm. And so we have these little incubators around all of these blood vessels coming up, particularly the carotid vessels. And we can warm all of the blood up before it gets to the brain. That is admittedly a little speculation, but I'm confident in it. Sex hormones largely determine where a person stores their fat. And when you look at a little boy and a little girl who are growing up, they look identical in their body shape. There's no difference until they reach puberty. And then the moment the sex hormones come into play, the sex hormones, among the many effects they're having, metabolically speaking, determine where the body will store fat. They're literally, like estradiol is literally enhancing the expression of enzymes that will dictate fat storage at breasts, hips, and buttocks, the kind of prototypical female sites. Whereas the androgens are largely inert. They don't really promote fat storage anywhere, but the only hint of it is centrally, abdominal. Now, all of that is white adipose tissue. Anything you can pin, and that is particularly true in females, because females relatively store so much more of their fat as subcutaneous fat than males do. Part of the androgen effect of fat storage is a little more visceral fat. So that's the fat that is enmeshed around the organs behind the muscle of the stomach. But but the estrogen's effect on fat storage is overwhelmingly subcutaneous. And that's good because, one, subcutaneous fat produces more leptin than visceral fat does. And two, if you have a woman who's storing a lot of fat viscerally, especially during her reproductive years, it may complicate the fact that you're about to grow a baby there. And now that the fetus is in the growing uterus is competing for very limited space with all of that visceral fat tissue. The visceral fat would be like actually pressing in on that very area. And so it's no surprise to me that the female phenotype is designed more to store fat subcutaneously because it gets the fat out of the way of that critical area on her body for fertility. Women do naturally have a higher set point for adipose tissue. It is supposed to be that way. Part of it is the necessity for leptin. Women's female fertility is much more dependent on a higher amount of leptin than male fertility is. And I believe, here's a little more speculation, but it's informed, that that reflects the fact that the female body bears the metabolic burden of fertility. The male has a brief, wonderful moment, and then his role in essential role in fertility is over. Now, I would submit that the dad has a profound role through the life of the child, of course. But even still, the burden, if you will, and I don't want to use that term may be too loaded because having had a wife who was pregnant multiple times and we have beautiful children, it's also incredible, but it is a burden on her body, a metabolic burden.
It's physically and chemically demanding.
Yeah,
absolutely.
Yeah, good.
Yeah.
Right. Yeah, you said it. That's right. So her body carries that metabolic burden. And basically, my thought is that her brain needs to know that there's enough fat on her body to carry that baby, to develop that baby, to gestate that baby, because her metabolic rate will be higher during pregnancy than it has been at any other point in her entire life. Because she is working so hard to grow her own tissue and to give the energy to the baby to grow the baby. And then even when baby's born during lactation, her metabolic rate stays very, very high because she's still producing enough energy for two. It's basically the brain's way of saying, hey, fat cells, is there enough of you that if we suddenly had reduced access to food, you have a lot of fat on you and we can carry this baby? Now, that I don't mean to assume like starvation. That would, of course, be a big problem. But it's basically the brain's way of ensuring there's enough stored fat that it is okay allowing fertility to move forward. and that is through leptin. If there's enough fat cells, there's enough leptin going to the brain, and the brain will turn on this gonadotropin pathway, going to the pituitary, then going down to the ovaries and telling everything that it can go forward. If there's not enough fat cells, there's not enough leptin, then the brain will shut that pathway off. It will turn off that axis of that gonadotropin releasing hormone from the hypothalamus, and then everything downstream of it. The pituitary will turn off its follicle stimulating hormone and luteinizing hormone, and the ovaries will just reduce all of those sex hormones. And then fertility would stop, ovulation would stop. That reflects the fact that her body bears the metabolic burden, not only of the gestation, but also of the lactation and feeding the baby. And so it's no surprise that it's a very, very complicated affair. But all of it, even still, comes back down to the humble and often misaligned fat cells. Insulin resistance has two aspects of itself. One is the pathological side, which is the version of insulin resistance which promotes chronic disease, these so-called plagues of prosperity, Alzheimer's disease, fatty liver disease, hypertension, heart disease. All of those are consequences of insulin resistance and the pathological version of it. But there is a physiological side of insulin resistance, which is when the body becomes acutely insulin resistant to serve a specific purpose. And that is the insulin resistance that we're touching on now when we talk about the changes, particularly during the menstrual cycle. So a woman will become relatively a little more insulin resistant. It's right as the endometrium is kind of at its thickest and progesterone is peaking. Then she is at her peak insulin resistance during that cycle. Now, it does not get to the point of like clinically problematic. But if her insulin resistance were humming along throughout the month at a very, very low level, or let me say it another way, she's very insulin sensitive throughout the entire cycle. And then with those few days, right around the time of ovulation and progesterone has come up, then she becomes a little insulin resistant. And then as she starts to shed, there's no implantation, no fertilization, then things go right back to insulin sensitive. The estrogens tell the body where to store fat, but not how much fat. That's very, very important. Overall, estrogen actually has a fat burning effect. This is why at any moment in time, a woman is burning relatively 40% more fat than a man is. Now, a man has a higher metabolic rate just because he's bigger, but a woman, relative to her body weight, will be burning 40% more of her energy from fat. And that is very, very heavily dependent on the estrogens. So estrogens tell her where to store fat, but also tell the body to rely on that fat. So a lot of fat is going into those fat cells, but a lot of it's coming out to be burned. So there's a high turnover. That's a very healthy way to store fat. Progesterone tells the body to store fat, and it does so by leveraging insulin. And so during that period of time, progesterone promotes a slightly insulin resistant body, and that means insulin levels have to come up a little higher to overcome this subtle insulin resistance, throughout the entire body. But that doesn't happen at the fat cells. The fat cells do not become insulin resistant. And so now this higher than normal insulin promotes a slightly greater than normal fat storage. So hormones like progesterone and insulin tell the body how much fat to store, whereas the sex hormones, progesterone's a sex hormone, so the estrogens and androgens tell the body where to store fat. And those are not the same thing, of course. So there is that acute little moment of insulin resistance, nothing to be concerned with. After her fertile years have passed her by, and as you noted, at that point, the aromatase expression changes in the ovaries, and her estrogens production starts to drop a lot. At that point, she's lost that kind of fat-friendly and even protective effect of the estrogens, and now she's sort of subject to the whims of the androgens a little more with regards to fat storage. Now, this is not to say her androgen levels go up really high. No. They don't change that much. It's just that the estrogens
it's a relative amount.
That's right.
Relative amount, yeah.
Perfect. That's perfectly right. And so now her body just starts to store fat in more of an androgenic way. In other words, as you perfectly mentioned a moment ago, more centrally. And she can literally start to lose some of that fat that she had been storing on her breasts, hips, and buttocks, because the estrogens were what was determining where that fat should be stored. And that then starts to, in a way, that at that point, the woman starts to lose the metabolic protection that the estrogens had provided her. Estrogens, in a way, provide a metabolic protection for a woman, allowing her to basically avoid the consequences of her fat tissue, the metabolic negative consequences. She's been protected from it. Estrogens help her body know what to do with fat and handle the fat in a good way. With the loss of those estrogens during menopause, now she's no more protected from the fat than her male counterpart is. Her risk of disease from fat tissue starts to match that in the males. If you were to take a fat biopsy from a woman and a fat biopsy from a man, and if you were able to put those fat biopsy tissue, the fat tissue, in a little beaker in a science lab and keep the tissue alive and active, it would literally be secreting 40% more of its fat at any moment than the fat cells from the male, from that same location. You pop it out of the belly. So you invoking the muscle, that could be part of the demand. In other words, the pull, where there could be a differential expression from the female muscle cells. I don't know this, so I'm speculating, but muscle tissue releases a myriad of hormones as well. And it could be that that there's a difference in expression of hormones, hormones like FGF21, for example. That is a muscle-derived hormone that can activate lipolysis. I don't know about that. I can't speak to it, but I do know that the estrogen effects simply enhance lipolysis on their own. So we can remove the muscle from the equation, although in the whole body we can't, and I believe it's very likely relevant. But just sticking with the sex hormones and the fat cell, Estrogens simply activate lipolysis at a higher rate, especially at subcutaneous fat cells. And the differences go even further. The estrogens not only tell the body where to store fat, but also how to store it. One of the reasons females can store more fat than males pre-menopause and be much, much healthier is that the very nature of her fat cells is different because of the estrogens. Estrogens, specifically, particularly at the buttocks and hips, much to the woman's dismay perhaps, provide an almost limitless phenomenon of hyperplasia. So anytime the insulin or the progesterone is telling her body to store more fat, because they control how much fat the body stores, the estrogens will tell those tissues, buttocks, the fat tissue in the buttocks and hips, hey, the moment the fat cell gets a little big, just recruit another fat cell and recruit another fat cell and another fat cell. So she continues to store her fat there by making new fat cells. That might sound like a problem, and it might be a problem if she's trying to squeeze into her college jeans that she used to wear. But metabolically speaking, it's magic, because when fat tissue is growing through hyperplasia, the fat cells stay small and they stay very metabolically healthy. In men who have relatively much lower levels of estrogens, there is none of this hyperplastic stimulus. And so his fat cells, if there is a pressure to grow, not through progesterone, of course, exclusively through insulin, they almost totally grow through a process of hypertrophy. And the fatter the fat cell gets, the sicker it gets and begins to promote insulin resistance throughout the body. So the protective effects of the estrogens go through multiple levels here, not only burning fat at a higher rate at any moment, but also altering the very nature of how she stores fat at those locations particularly. As she is storing more fat, her fat cell number starts to go down. But again, that's not a great thing, because that does mean, in the absence of any other changes, and Stephanie, you mentioned it very, very well, to me, there's an opportunity there for lifestyle change. But as she starts to lose her fat cell number, if she continues to eat the same way and live the same life, then her body still wants to store that fat. It just has to store the fat now in fewer fat cells, inducing a greater and greater hypertrophy, and perhaps storing the fat in tissues not designed for long-term fat storage, like the liver and the muscle, etc. So she loses multiple protective benefits. Again, that all plays into why I say estrogen allows the woman to be a metabolic superhero. And with the loss of that estrogen, she just becomes a mere mortal. When the fat cell gets too big, we almost have to feel bad for it, because it starts to try to survive. But the two ways that I'll mention in a moment in which that it leverages in order to survive end up, unfortunately, creating metabolic havoc for the rest of the body. When the fat cells are hypertrophying too much, they begin to actually push each other further and further away from capillaries, blood vessels. And the capillary is the site of exchange for a cell. It's where it gets new oxygen. It's where it dumps off its CO2 from its metabolism. It's where it receives new nutrients or gives out its nutrients. And so suffice it to say, a cell has to be very, very close to a capillary in order for that to work. But as the cells are hypertrophying so much, now it used to have maybe a micron or two away from a capillary. Now it's getting several. It's increasing multiples in distance. That is catastrophic. It will literally die. It will suffocate, and it will undergo a process called necrosis. It will rot and die, and we don't want that. So the hypertrophic fat cell, who senses that it's becoming increasingly hypoxic or reduced in oxygen access, it will start to secrete pro-inflammatory cytokines, because some of those cytokines will induce the production of new blood vessels. So this is the big fat cell's way of saying, hey, capillary, you're too far now. I'm sending you this message. Bud off. Branch off a little capillary to come out this way so that I can start to get some blood so that I don't die. Now, that helps the hypertrophic fat cell survive, but at the same time, it's secreted a whole panel of pro-inflammatory proteins, only some of which, largely one, is actually helping with the improved blood flow. But it just sort of belches them all out. And then it's all the rest of these pro-inflammatory cytokines that begin to promote a subtle but relevant inflammation throughout the entire body. Like the body is fighting a mild infection in the absence of any actual infectious agent. It's just this fat cell doesn't know what else to do. At the same time, the fat cell is reaching a point of maximum dimension. And I know of no comparable effect where you can take a normal sized fat cell and in the presence of insulin to promote its growth, it can grow to 10 times its volume. And unlike any other phenomenon in the body, where it will grow 10 times. And at that point, it begins to reach a point of maximum dimension where it simply starts to tell itself, I can't grow anymore, or I will overwhelm the ability of the cell membrane to hold us all together, and we will literally burst apart. And so the hypertrophic fat cell starts to tell insulin, you want me to keep growing. And so while I can't stop you from shoving the nutrients in, because it can't really, I can stop you from preventing me from breaking down my fat and leaking out my fatty acids. So that's what happens. I know I got that a little complicated with a bunch of double negatives, but basically insulin would tell the fat cell, don't break down any fat. In other words, inhibit lipolysis. Lipolysis is the technical term for breaking down stored fat. But the hypertrophic fat cell says to insulin, I can't stay this big. I can't continue to grow like you want me to. So fat keeps coming in, but now the hypertrophic fat cell starts letting fat out.